We've done our first two. Let's look at some other possibilities of how we can generate text. And by the way, for those of you who haven't looked at Lab 6, you do have to write a greedy. So you'll be calling the RNN just in the way we talked about. And you have to write a greedy, you have to write a beam search, and you'll also have to do this next approach I'm going to use. So the next approach is stochastic. And let me see, what did I call it? I just called it, let's say, random sampling. So in random sampling, we have a bunch of probabilities. Why don't we just generate a word based on those probabilities? So we will flip a coin with a 40%, a fancy coin that somehow has all these probabilities. But we flip a coin with 40% chance we'll choose so, with a 20% chance we'll choose very, and so on. So for random sampling, choose a word according to y hat, and just keep going. If I call it 10 times, how many different unique sequences will I get out?
Well, you could get up to 10, right?
Yeah, I should probably get up to 10, right? Because we have this stochasticity. So, and can I generate multiple sequences simultaneously? So can I generate 10 different sequences for roughly the cost of one sequence? Actually, that's not, I wasn't even clear about that for beam search. So beam search, if K is small enough such that a batch can fit in GPU memory, then a beam search is about as cheap as a greedy search. Certainly the same number of calls to the RNN, right, as a greedy search, because I can use batching. And I can use the same batching for random sampling. I guess I could also keep track at the end of what the probability, what the total probability was of having generated the sequence. So maybe I had a very unlikely choice of a word. You know, I chose this 0.001 word, and so I could find out this was very unlikely. One thing you may find here is that you want to adjust the probabilities in some way. So you may want to, for example, accentuate the higher probability things at the expense of lower probability things. So you can use what's called temperature. So basically what you do is scale pre-softmax. The fact is, what normally comes out of an RNN is not a softmax. You actually normally will get out the raw values. And if you remember, the way we compute a softmax is we say e to the y hat sub I over the summation of all of the e to the y hat sub i's. So we're getting y hats in the range negative infinity to positive infinity, and then this is the softmax operation that is going ahead and scaling them to be between 0 and 1 and summing to 1. The temperature constant says basically, why don't we apply a multiplicative factor? So let's say we have a temperature constant T. We're going to go ahead and multiply T times each y hat before we take it to the e power. If you have a T equals 1, Tom, what does that do to the softmax?
It's just...
If anything.
Say that again, sorry. What did you say?
What does it do, if anything?
It does nothing.
Yeah, so it does nothing.
Yeah.
And why don't we do another one? What if T is greater than 1? What is that going to tend to do?
Emphasize
So if I have
the difference between the prediction.
Yeah, it's going to emphasize, it's going to make high probabilities higher and low probabilities lower. So if you had a probability distribution that looked like, assuming for, well, let's just say it's like that, then it would make the high ones higher and the low one's lower. Okay, this is not to scale, it just gives kind of a rough idea, right? Because we have this power factor, right, this exponentiation. So the e to the whatever makes the bigger ones big and the smaller ones smaller. And if t is less than 1, Ben, what's that going to do?
It's going to pull everything close together, basically.
Yeah, it's going to make them more even. If you want to have a random sampling, in fact, we can set t such that random sampling is the same as greedy search. What would we set t to? If we set t basically to infinity, you're going to get the highest one is going to get probability approaching 1, and the remainders are going to get probability approaching 0. So our random sampling will approach the greedy search as t gets bigger and bigger and bigger, so that it will just be favoring the highest probability. On the other hand, if you reduce t below 1, that's going to tend to have more, what would we call it, creative output, right? Certainly more different from run to run. Does that make sense?
I'm not sure about how the higher the t value is. How does it make the lower probabilities lower?
It makes the lower probabilities lower because their value in the summation matters less, right? Because our total sum is going to get bigger more for the larger ones than it is for the smaller ones. Or maybe another way I can put it is if I have a probability distribution and I increase any one higher, it's got to force the others lower, right? Because our total has to still be 1. So as long as you can see how high probabilities get higher, it's got to be low probabilities get lower. And in fact, right, the highest probability goes up more, the next highest probability goes up some but less, and so on. So as this is one of the parameters that we'd use when you are generating samples, you're trying to generate Shakespeare text to try and get stuff that looks good,